let's recall what we have discussed last time. So discriminant function. So this is a common way to represent a classifier using discriminant function. So from now on, we are talking about learning a model that represents the membership of the classes. So say you have k plus 1 classes, then you're going to have k plus 1 membership function or discriminant function. And one of the easiest approach you can make is using all of the k plus 1 function so that you can find out the largest estimate value based on the instance x. So what you need to do is choose class number c that maximize this discriminant value. So based on that, we talked about binary classification. So say you have two different discriminant functions, one is for 0, the other is for 1, and the membership is determined by the size of the quantity. So when output of G1 is large, it's going to be red in this example. If G0 is large, then it's going to be blue in this example. And naturally, this decision boundary is determined by equating these two functions. So those area in the data space where the value of G1 and G0 is the same, this is going to be your decision boundary. So given that, although we haven't discussed this last time, we could actually build a easiest form of a classifier using linear regression model. So linear regression model, well, as you remember, this is for the real valued target, but we could build a classifier out of it. So let's assume you have two linear regression models. So one is G0 Wx, the other is G1, another Wx. So each of those vectors, they are indicating the class membership. And for those positive classes, so those who are labeled with 1, you want to plug in those data in this way. So x and 1 goes into G1. And same x, but you're going to modify the output value. So x and 0 is going to G0. So the positive instances, they are going to pair with label 1. And same data values, they are going to pair with G0 with the label 0. And let's think about another half of the data set. So data set with label 0. Again, G1 gets the data with the original label value. So you have negative instances which are labeled 0. They are going to G1. But on the other hand, where these are same data, and you have negative instances, and you're going to modify the label to be 1. And this is going to get back to G0. So eventually you're going to draw some line. A bunch of data, they originally belong to Y1 and Y0. And you want to draw some line like this. So this is the regression model. So you want to draw a line. And that is well, ranging between Y0 and Y1. So this is G1. And let's talk about G0. So original label of the data was positive, but you modify the label to be 0. And original label of the data was negative, but you labeled the data with 1. And now you want to draw a regression line like this. So you have two models, and you can obtain this line using least square. So this is a linear regression. And at the end of the day, if you have a new data falling into the positive class, well, it will return some value close to 1 from G1. But the same instance result in some value close to 0 from G0, because that's the way we train the model. So by exploiting this property, we could build a classifier like this. So the same decision rule can be applied to this kind of ad hoc construction of the classifier. So by doing that, we could build a linear classification model using linear regression algorithm, where we could be more simpler. So in the previous case, we had two sets of vectors. So one, another. this requires two sets of weight vectors, but we can make some modification to have only one set of the weight vector by setting G1 is equivalent to negative G0. So instead of building W1x, W0x, from now on, we are going to define G1 as WTX and G0 is negative WTX. And in the training time, you only need to train G1. And for positive classes, you want to train W by setting Y is 1. For negative class, you want to train W by setting Y is negative 1. So this is going to be more simpler. You have positive instances and their label is 1. And you have negative instances, their label is negative 1. And you're going to draw some linear regression line like this. So from now on, you can make a classification based on the sign of the output. So when the sign is positive, then it's going to be class 1 or positive instance. Sign is negative, then it's class 0 or negative instance. And this makes a little change in terms of the notation in the same decision space. So when G1 output positive, it's going to be label 1. And G1 output is negative, it's going to be label 0. And WTX, where it is equivalent to 0, that's going to be your decision boundary. So you could build a linear classification model using the same linear regression algorithm. So you don't need to develop a new algorithm to build a classifier. Well, maybe that's a sort of good thing. But at the same time, it has a limitation. So regression is related to Gaussian distribution. So where each time you are building linear regression model, you are assuming there's a Gaussian distribution behind the entire data set. But speaking about Gaussian distribution, it's going to define the data space in terms of the real output value. But in our case, we are going to classify the data in terms of 0 and 1. So we have binary label, and this is different from Gaussian distribution. And moreover, sometimes we want to estimate the probability. So you want to measure the confidence. So we want to estimate the probability of y being 1 based on the observation x. Well, using the model that we just defined. So linear regression model does not give us any probabilistic output. So we cannot estimate this confidence value effectively. So let's try to think of a little bit more modification in the previous model. So instead of using a linear regression line, let's try to consider some additional add-on top of the previous model. So what we want to do is putting some additional function called the logistic function. So instead of putting the decision along with the line, we want to add this S-shaped line. And this is simply making some switching. So like the unit step function, it's going to switch between one label to another label. So based on the input value, we want to make a decision where you fall in. But at the same time, we want to be smooth. But the purpose of being smooth is to obtain the model using gradient-based method. At the same time, well, let's think about the decision made on one extreme. So the decisions made on the extreme side, where maybe you're sort of for sure. So this is class 0, the other is class 1. Well, the ones that we are confusing and we want to estimate the probability from, they are maybe around somewhere in between. So using the smoothed curve, well, that are located in the middle between two different decisions, we can estimate the probability. So the outcome of this logistic function represents probability. One additional property that made this possible is the outcome ranges between 0 and 1. So all the probability value range between 0 and 1. And logistic function satisfy that condition. So we talked about the property of a logistic function. So from now on, we are going to use this kind of function on top of our decision Wx. So Wx gets in as the input to the logistic function. In other words, this is sigmoid function. And this sigmoid function is defined as this. So 1 over 1 plus e to the minus c. So we are going to plug in this WTX to sigmoid function. So it's going to be eventually like this.